We're continuing to look at parallel charge plates, and another aspect of these that's interesting to identify, as you can see here with the relationship between electric field strength and surface charge density. We'll talk about surface charge density in a second, but before we do, just want to draw your attention to a few properties that we can look at with charge plates. First of all, we've already seen the distance between them is an important characteristic to consider. Another one to be aware of is the area. So if we're talking about the area of this whole plate, and keep in mind that that's a plate, so if we were to represent it in 3 dimensions, it would look something more like this. And so the area that is involved would be important to consider. And the other thing to consider is the charge Q that we would find on each plate. Now the amount of charge will be the same on each plate, so we'll just use the value of Q to represent the charge on the plate. Now what we're going to do here is just consider the effect of each of those variables on the charge on the plate. Now there is an experiment in the text that looks at these relationships, but we won't be doing that. There's need a power supply that we don't have, so we'll just do this theoretically. So first one, if we look at the potential difference, so if the value of this EMF at the bottom here is increased, if the increases, it makes sense then that if you've got a greater potential here, you can push more charge onto each of those plates. So that means that Q will increase. So that's keeping the area and the separation D the same. That means that we have a proportional relationship, so Q is directly proportional to V. If the area increases, so if we've got a greater surface area across the plate, then it means that we can push more charge onto the plate, and so again Q increases. And again, Q there is going to be proportional to the area. Now this one's a little bit tricky to make sense of, but if we think about the potential difference being the same, the area being the same, but we increase the distance between the charges, that means that distance between the plates, it actually means here that the amount of charge will decrease. And the easiest way to think of that is to consider that the further apart the plates are, the less repulsive forces there are, and so there's not as much charge. Something just to be aware of. It's not something that you need to memorize, but just to develop this relationship that we need to look at here. So we have those quantities, or those relationships relating the charge to each of the variables there. If we combine those into one equation, we can see quite easily what the relationship, how they'll tie together, and there will be a constant of proportionality here, and it's one that you've seen before. So first of all, we're going to have that Q will be equal to V times A divided by D, and the constant of proportionality here is epsilon naught, which you've seen before. It's the permittivity of free space. I'm not going to go too much more detail into that, but we can always talk about that more in class if we need to. Now, coming back to that idea of surface charge density. Surface charge density is one of those properties that is useful to be aware of under certain circumstances. The symbol that we use for surface charge density is a lowercase sigma. That's now defined as the term suggests, the quantity of charge per unit area on the plates. Quantity of charge per unit area. So we'll talk specifically here about plates, but you could have surface charge density of any any shape, whether it's a plate, whether it's a sphere, doesn't really matter. So that sigma will then be equal to Q divided by A. And if we look at the equation that we just had before, we can easily produce that Q divided by A by dividing both sides by A. That means actually we'll be left with epsilon naught V on D. Now, hopefully you can recall from the previous video that electric field strength is equal to V on D. So that means that our surface charge density is actually equal to epsilon naught multiplied by the electric field strength between the plates. Or if we write that in a different way, we can say that the electric field strength is given by the surface charge density divided by the permittivity of free space. So the useful thing here is that we now have a representation of the electric field strength that only depends on the surface charge density, not on the potential difference between them or any other factor. If we know the surface charge density, we can figure out the electric field strength between the plates. One last thing to identify here then, if we consider this electric field strength, that electric field is actually the resultant of the electric fields produced by each plate. What I mean by that is that while we've been dealing with the electric field strength between the plates, and we've sort of been dealing with that as a given, we've really got two charged objects here, so each charged object is going to have its own electric field around it. So if we consider let's imagine we charged up a negative plate and that was all we had, so we had a plate that was negatively charged, then we know that the field around that would look like this, with the field lines going in towards it. If we had a positively charged plate somewhere else, then it would have field lines that would be directed away from it. Now, if we were to consider what happens when we bring those two things close together, we can identify that the resultant then is just the sum of these two fields. That means then that the electric field near a single charge plate will simply be half of that value that we've got at the top of the screen there. So it's going to be E will be equal to sigma over 2 epsilon naught, so half of the value that we had. And if you think about that, if the field in this region here was given by that quantity, and the field in this region here was given by that quantity, then the total would simply be, let's call this E1 and E2. That would be E1 plus E2. If they both have the same surface charge density, then it's going to be simply that value added twice, taking into account the vector aspect here, and you can see in the region that would be between these two, it's both in the same direction, and so we get sorry, get rid of that too. Add those two together and we get the result that we've got at the top of the screen. So if we have a single charge plate now, we can actually figure out what the electric field strength is just by using the surface charge density on the plate.